Hi, this is Kenny Lee, and let's talk about capacitors in series. Now, there are some properties with capacitors in series that match up to resistors in series. First of all, the charge on each capacitor will be the same, just like the current is the same through each resistor in series. The potential difference across each capacitor may be different, just like the voltage drop across each resistor may be different for a series circuit. If we add the potential difference across each capacitor up, it should equal the voltage from the battery. The total capacitance of capacitors in series is the sum of the inverses. So this looks similar to resistors in parallel, but this is actually capacitors in series. So let's do a couple examples to see how this works. So we've got two capacitors connected in series to a 12-volt battery. We want to find the total capacitance, the total charge, and the potential difference across each capacitor, because we know the charge will be the same on each capacitor. Capacitors in series, we got a battery, one capacitor, and then another capacitor. Now don't get this confused with parallel, because this one there's only one line going from one side of the battery to the other. So these two capacitors are in series with each other. Okay, for this one we've got a 12-volt battery, a 250 microfarad capacitor up there, a 400 microfarad capacitor here. And so to figure out the total capacitance, we simply add the inverses. Since both of them are with the same unit, they match, then we can just do this, and then we can take care of the microfarad stuff later. So 250 inverse plus 400 inverse this. And so we get a total capacitance of 153.85 microfarads. So that is 153.85 times 10 to the minus 6 farads. So that's the total capacitance of the circuit. To figure out the charge, we've got capacitance equals charge over potential difference. So 153.85 times 10 to the minus 6. And we need to go ahead and put it in that form to do this. We want to know the charge, and we know the voltage is 12 volts. So 153.85 times 10 to the negative 6 times 12 gives us a charge of 1.8, let's call it 5, times 10 to the minus 3 coulombs. Now to figure out the potential difference for each one, we're still going to use the same equation. C equals Q over V. This time we're actually going to find V. We know the capacitance, the first one, is 250 microcoulombs, so times 10 to the negative 6. The charge on each one will be 1.85 times 10 to the minus 3. We got to figure out the voltage. So switch things up, what I call the super secret metric. That stays on top, and that takes the V's place on the bottom. So 1.85 times 10 to the negative 3 divided by 250 times 10 to the negative 6 gives me a voltage of 7.4 volts. That's the potential difference across that one. Let's do the other one. I'm going to do it down here where I have a little bit more space. C equals Q over V. Same thing. 400 times 10 to the minus 6. Charge is 1.85 times 10 to the minus 3. And we've got to figure out what V is. Switch them up. So we get 1.85 times 10 to the negative 3 divided by 400 times 10 to the negative 6. We get 4.625 volts. Now to check our answer, add these two together. So I add 7.4 to that, and we get 12.025 volts, which pretty much matches the 12 volts that we started off with the battery. We got a little bit over simply because we rounded. But if your voltages here add together to equal the voltage from the battery, you pretty much know you got the answer right. All right, let's try another one with capacitors that are more drastic in difference. So here we've got a 2 microfarad, a 40 nanofarad, and a 200 picofarad capacitor connected to a 24 volt battery. All of this is in series. So we have our battery, one capacitor, two capacitors, three capacitors, and back to the battery. So that's 24 volts, 2 microfarads, 40 nanofarads, and 200 picofarads. In a parallel circuit with capacitors, the largest capacitor kind of dominates the entire thing. But in series, it's actually the smallest capacitor that dominates things. So this 200 picofarads is actually going to control what's going on in this circuit. And we'll see why when we figure things out. So first thing, I want to figure out total capacitance. So 1 over CT equals 1 over 2 times 10 to the minus 6 plus 1 over 40 times 10 to the minus 9 plus 1 over 200 times 10 to the minus 12. And then we have to flip it. So 2 times 10 to the negative 6 plus 40 times 10 to the negative 9 plus 200 times 10 to the negative 12 equals is 1.99 times 10 to the minus 10 farads. I almost forgot to invert it that last time. That's a common mistake. When you add these up, they're going to give you 1 over CT, or 1 over the total capacitance. So you have to invert that one more time to get this. And here's another secret. The total capacitance is always going to be smaller than the smallest capacitor that you have in here. So it's got to be smaller than 200 picofarads. And that is. So we're good. 200 times 10 to the negative 12 is 2 times 10 to the 10th. This is slightly smaller, so that's a good sign to start off with. But that's a good way to check your answer to start off. See if you're heading the right direction. All right, let's figure out the charge. So C equals Q over V. Capacitance 1.99 times 10 to the minus 10. Charge we don't know, but our voltage is 24 volts. So 1.99 times 10 to the negative 10 times 24 gives us a charge of 4.7, let's call it 8, times 10 to the minus 9 coulombs. That's a 9. Now let's figure out the potential difference or voltage drop across each capacitor. So I want to start down here so I have enough room. So for the first one, C equals Q over V. Capacitance is 2 times 10 to the minus 6 for the first one. The charge, remember all these have the same charge, so the charge on this one is 4.78 times 10 to the minus 9. We got to find the voltage. Do my super secret math trick again, where we flip those. This comes out, that goes underneath. So 4.78 times 10 to the negative 9 divided by 2 times 10 to the negative 6 gives me a voltage of 2.39 times 10 to the minus 3 volts. That's really small. Let's see what happens to the rest of them. So for the second one, the 40 nanofarads, C equals Q over V. 40 times 10 to the minus 9 equals the charge, which is 4.78 times 10 to the minus 9. Swap these two. So 4.78 times 10 to the negative 9 divided by 40 times 10 to the negative 9 gives me a voltage of 0.1, let's call it 2 volts. And for the last one, C equals Q over V. Now for the 200 picofarads, 200 times 10 to the minus 12. Charge is 4.78 times 10 to the minus 9. And we got to figure out voltage. Again, swap. So 4.78 times 10 to the negative 9 divided by 200 times 10 to the negative 12 gives me 23.9 volts. Well, let's just double check. So the voltage across these should add together to equal the voltage from the battery, which is 24. So we got 23.9 plus 0.12 plus 2.39 times 10 to the negative 3 equals 24.022, which is just a little bit over 24 volts. So that's probably a rounding difference, so everything looks good. But remember that check. It can help you out a whole lot to make sure that you are going along the right path. Thank you very much. We'll try a compound circuit with capacitors and see what that looks like. Thank you. Tune in again and like, share, subscribe. Goodbye.